Okay, let's look at our rotating cube, and we're going to look at a couple of ways to do that, and later on I'll build on this example, adding texture mapping, adding shading, and a few other little tricks. Let's take a look at it. What I want to do is put it all together, everything we've talked about modeling and some of the code development we've been doing, and look at two different ways of doing that display. First, by drawing arrays, which is what we've been doing in our other examples, but a more efficient way is to draw it by elements, which brings in the kind of modeling that we talked about in the last lecture. So let me just show you where we're going to get, and I'm going to do this in stages. So let's see if I can do a little display and bring this up. Yeah, so here's what we're trying to get. I'll eventually put some buttons in here to change the direction of rotation. I'll do this with solid colors too, to show you how it's just one line difference. But notice here we're using interpolation by assigning one of the 6 colors, cyan, magenta, yellow, red, green, and blue, to the vertices, and then having the rasterizer interpolate those colors across the triangles, 2 triangles per face. Okay, but we'll come back to that and do it. I'll build this up with a cube first, then we'll add the rotation a little bit later. So let's come back to it. Let's start by saying, okay, let's look at the vertices first, and we can just put them in an array. And I've sort of rigged the example again, so we're putting everything in clip coordinates for now, so I don't have to do transformations. Starting later this week, we're going to be talking about viewing, and then I'll bring in the model view transformation and how we can start in any coordinate system and then scale things and position things so we get into clip coordinates. But let's start with things in clip coordinates, remember, which are go from -1 to 1 in x, y, and z. And let me start with the 6 colors and put them in a color array. So we'll have black and white in there, but the ones I'm going to actually use in this example are red, green, and blue, cyan, magenta, and yellow. So we define them as just, again, as simple arrays. And notice we're doing this in two ways. It really doesn't matter much in the examples. Here I'm building the vertices out of the Vec3 type. Here I'm building them out of an array of JavaScript arrays. As you'll see, it really doesn't matter because underlying this representation is the use of JavaScript arrays. Okay, so there's the base. Now let's come back to where we were before at the end of the last lecture and said, okay, we're going to separate the topology and the geometry, and here's the topology, which says, okay, a cube is made up of 6 quadrilaterals, and we can describe those 6 quadrilaterals through some function we're going to call, where we just give it the vertex numbers, and we'll note that all of these 6 faces are numbered, so they obey the right-hand rule, which is that they encircle counterclockwise when looked at from the outside. So 0, 3, 2, 0, 0, 3, 2, 1. Here's 2, 3, 7, 6. And again, repeating from last time, it's the order that matters, not where we start. So 0, 3, 2, 1 and 3, 2, 1, 0 are the same as far as this is concerned. Although we will use the first one to pick a color when we want to display the cube as solid colors rather than interpolation. So if we want to have different colors on each face, I'm going to want to have something like, if I don't want to use white and black, I want to use 1, 2, 3, 4, 5, 6, and so I can reorder these so that I get 1, 2, 3, 4, 5, 6 here. Okay, so now let's look at the various parts of the code. We know we're eventually going to have to put everything in terms of triangles. So we know that even though we have 6 faces, each of the 6 faces is going to be modeled as 2 triangles, and that gives us, so we have 12 triangles, which means we're going to have 36 vertices. Here's just initializing the point and the color arrays, which we just actually I can put all of that code from the last couple of slides right here. this part here is going to be exactly as we've had it before. We're going to initialize exactly as we've done before, is by setting up the buffers on the GPU, one for colors and one for the vertex location. So I'm not going to copy that in. The HTML file will be exactly the same because I'm going to use the same simple shaders we were using before. So this part here is the same. Maybe the one part that might be different here is I need to do the depth test because I want to use the Z-buffer algorithm, so I only display the front polygons, not in the order in which I generate them, but rather in the order in which they are in terms of where the viewer is. Okay. Now the quad function is the more interesting thing, but notice how simply we can do that in JavaScript. So I can say, okay, here you have a quad with vertices A, B, C, and D. I know I have to break that up into two triangles, so actually I don't, because a more efficient way would be to do this whole thing with triangle strips or triangle, the other form of triangles where we keep the one point, a triangle fan. But we're going to do two triangles. So the first triangle, if we think of this encircling A to B to C to D, the first triangle could be from A, B, C, and then back to A. And then the second triangle could go A diagonally up to C, and then to D, and then back to A. So I could say, okay, here's a set of indices for the two triangles. And what I'm going to do is for those vertices, I'm now, see, these are now pointers, really. And I'm going to now say for these, and how many are there? There's 6. You know, again, using the JavaScript length function for the array, it says, okay, for each of those, I'm going to push a vertex onto a stack, onto the point stack, and I'm going to push a color onto the color stack, and that's it. And now, which vertex am I going to push? I'm going to push the ith vertex from this list, and colors are, I'm going to point to in the same way. I'm going to put in the ith color. So I put in vertex, for vertex A, it'll be 0, 1, 2, 3, 4, 5, or 6, or 7, and I'll put in that vertex in that color. Now let me just show you that and I'll show you this later, to get, now this is assigning a different color based on the vertex number to each vertex. If I want to use the same color for the entire face, all I have to do is push the same color for every one and just use the color of the first vertex. And it's just one, substitute this line for this line, and now you get solid faces, and I'll show you that in a little bit. Okay, so that's simple. What about rendering? Rendering is pretty simple. I'm just going to clear the color buffer. I'm going to clear the depth buffer, and then I'm going to render those triangles that, because there's 12 of them, it's going to be these 36 vertices. And then I really don't need this because I haven't done any animation yet, but it's safe to put this in. Just says keep rendering. Okay, now let me give you a little bit different way, and that's also on the website. And what I want to do is now look at this by looking at the indices and trying to draw things by the index numbers. In other words, what I do is I send all the data over in this form over to the GPU, and it's in a pretty dumb form. There's no structure. It's just triangle, 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 triangle in the GPU memory. Let's see if we can do better than that, which is going to be especially important when I try and make use of the fact that edges and vertices are shared by multiple triangles. So let's suppose I do the following. What if I make a list of indices for this? And these are the indices of the 12 triangles. There's a triangle that goes from vertex 1 to vertex 0 to vertex 3. A second triangle goes from 3 to 2 to 1. These are actually the two triangles that we use for the face that is described by quad of 1, 0, 3, 2. So all I've done is break it up into two triangles in terms of the indices. So here's the second pair of triangles, the third pair, and so on, and I put them in an array indices. Now these are called the elements, And what I'm now going to do is do a slightly different way of actually describing the information, because it's all here. This is telling me everything I need to know about that, as long as I have the geometric locations of the vertices. So let's see how we do this. It's called rendering by elements. So what I'm going to do is create, I have to get this information over to the GPU, so I'm going to create a buffer. It looks sort of like the other buffers, one small change. And I create the buffer. I'll call it the I buffer for the index buffer. I call it, now it's a different type. It's not an array buffer. It's an element array buffer. So it's telling the GPU that what I'm putting in there is not just the vertex locations. It's something else, and the element array buffer. So now you can see there you have two options for this parameter, so we really needed it. Now, what is the data that's going to go in there? It's going to be those indices. And what I need to do with those indices is now put those indices into a typed array, which is just a 1 byte. In terminology of typed arrays, it's a uint8. It's a 8-bit integer, which is just a 1 byte. And so I want to now create a new uint8 array, and in it go the indices. Okay, so the point here is that I don't want floating point numbers in there. I want bytes. Why do I want bytes? Because that's what OpenGL wants to see in the GPU. So this is to get. So notice I don't have the flatten function here. You can create a function that does it, but this does it to get bytes over there. But this is a very, very simple way to do it. So I'm sending this array over here over to the GPU as a list of bytes, for those integers. If I'm only going to do it once, we'll do static draw. If I'm going to do the more dynamic version, I could use GL static draw when I start animating it. Now, the only other change I have to make, I'm still going to send the vertices and the colors over exactly as I did before as array buffers, but the render is different. To render now, I'm going to render the triangles. I'm going to give it the number of vertices, the 36, and unsigned byte, because that's the form that I've put these indices in. Because what I'm doing now is not drawing arrays, I'm drawing elements, and the GPU is now saying, oh, I'm going to translate these elements over into those buffers that you gave me that have the vertices and the colors. So it's very, very nice. It says, okay, let's send them, let's use those unsigned bytes to go back and do exactly what we did when we talked about vertex arrays. Now I can make this even more efficient by making this list even shorter by just giving it the quad indices and just say this is quads, and I can make them so I would have 1, 0, 3, 2 instead of these two elements. So I'd have 4 times 6, 24 elements in this index array. And then over here, rather than render them as triangles, I could render them as triangle strips or triangle fans, depending on which order I put those vertices in for each of the quads. And that I really say, try this out, try making that change, because when you do this in practice, you really want to get in the habit of using triangle strips. Triangle fans occur in special cases, but triangle strips are the ones that get used most often. So do that. Okay, now to finish up the example, let's just animate it. So what do we do to animate it? Well, as you saw in the example I gave you, I showed you at the beginning, I had 3 buttons in there to just switch which axis you were rotating about. So here's the basic code to do that. Define variables for the x, y, and z axis. Then the axis variable is which one you're now rotating about. We'll start it off as rotation about the x-axis when we start the program. We'll have three angles that we rotate about the x, y, and z axes. So in terms of what we were talking about before, this is theta x, theta y, theta z. I do the standard thing of setting up a uniform variable for theta, which is going to be in theta loc. Here's how I set up the buttons are really simple. This is the JavaScript side. The HTML side is exactly as we've seen before. And all it does is say if you click the X button, make the present axis be the X axis. If you click the Y button, make it the Y axis. And if you if you push the Z button, make it the Z-axis, and then that's conveyed to the render function, and the render function will increment the angle in theta corresponding to what axis is set to, and then send it over the whole theta over as a uniform variable, and then draw everything. So here it is. Clear each time through, clear the buffer, increment that particular direction angle by 2 degrees, send that over, all 3 angles over as a uniform, and then draw the arrays. Now this is assuming that that rotation matrix is actually being done, as we discussed in a previous lecture, inside of the vertex shader. So this is giving information to the vertex shader. The transformation is done in the vertex shader. We draw those triangles and then request an animation frame, so we keep going through this loop. So let me show you the one change real quickly, and then to end this lecture. So let's go back here to this. So here's our rotating cube, changing the axes around. I guess I don't really love the interpolated values, so let's come over here to the code and let me show you that one line change. Here's the JavaScript file. I uncomment this line, comment the above line. Let me save it, and I should be able to just reload, and look, lo and behold, we've now have solid colors on each face. I mean, this is one of the things I really like about working with WebGL. It's so simple to make changes in the code, save the changes, and just reload the file. Okay, so let's leave it there. Now I'm going to do one more lecture related to translations, which will be sort of an extra lecture on creating a virtual trackball, and then what we're going to do is move on to talk about viewing.